Alright, so this is the final project tutorial for Dr. Osbey. Um, Basically what we're going to be doing is walking through how to generate geometry for an airfoil with an aspect ratio of 10. We're going to be plotting some values, and then we're going to be plotting coefficients as long as angle of attack and induced drag. So let's get started. So we can open a new project and then hit direct foil design, go to foil, Naka foils, and in this one he wants 2415, so we can switch that to 2415. I'm going to switch this to about 200 panels. Okay, that should be good. We can see everything here, the center line, and we need to do now a direct foil design analysis, sorry. Go into analysis, batch analysis, and so we're going to simulate a whole bunch of Reynolds numbers. We're going to switch this from, so this will end up being a different value, but we're going to switch the analysis range from -6 degrees to 16 degrees for our angle of attack, because he wants us simulating um, that those different angle of attacks, and then these different Reynolds numbers. So with a bit of calculation, you can see that we're going to need a bit more for Reynolds numbers. So in order to add more, you can click insert after, and then this I have a lot larger of a number, 6 million, 3.3 million. And so we're going to do a polar type of T1. Everything else can be kept the same relatively. Uh, Close. I think we can hit analyze. This should run. Hit close. And then it's going to give us a whole bunch of different graphs for our airfoil. And now we can go into wing and plane design, and we can actually start modeling our wing. We're going to go into plane, define a new plane. Let's just call this one aspect ratio. For this video, he wants aspect ratio 10, I believe. Yes, aspect ratio 10. We don't need elevator or fin since we're just doing the main wing. We're going to define that. Chord length should just be 1 meter on both sides. There's going to be 0 degree offset, no twist, no. It should be all just a rectangular wing. You come down here and select the foil. And then so he wants an aspect ratio of 10. So you can see over here we have an aspect ratio of 2. So to increase it, this should be, I believe, 2.5. Sorry, 7.5. I was wrong again. 5.5. 5. Sorry. As always, you can always just play around with different aspect ratios by changing the these different values. Obviously, 7.5 was for 15 aspect ratio, and then 2.5 was for a 5 aspect ratio for the other parts of the project, which is where I got messed up. And then you can see this looks correct. We can hit save and then save, and we can come over here and You see the airfoil, how it looks from the side. From the top, it is just a rectangular airfoil. And then we can define an analysis and go over here, LLT, wing only, lifting line theory. He wants us at 50 meters per second. Sorry, 50 meters per second. And then you can see our Reynolds number here is correct, 3.333 which matches that Reynolds number that we had earlier. Everything else we can keep the same. Save. Usually this will be unchecked, but you want to check on sequence. Start at -5 to 15 degree angle of attack with a change of 1 degree. And we should be good to run the analysis. And there we go. That was pretty quick. These allow you to see different values, sort of like an ANSYS. You can just animate it. But what he wants for us to do is to plot different graphs. So we can come over here, and we have a bunch of different graphs here. So for our aspect ratio 10, obviously with the more planes that you create, you can see more. You can see all of the same values on the same graph. So he wants us to show CL versus angle of attack. So here it is right here. That matches the theory pretty closely with this stall lift coefficient not totally being in the region, but you have that lift slope curve right here that you can calculate. You can export it to Excel. In order to do that, you can right click here, current graph, and export, and you can export it as a Excel file and do a whole bunch of analysis in Excel. She wants a CL over CD versus angle of attack, which is this graph right here. The CD versus angle of attack, let's see, right here. So, which makes a lot more sense as the wing increases in angle of attack. The frontal area is increasing, so you're having a lot more of a drag coefficient, induced drag, skin friction is being applied to the wing. We also have our efficiency here, our Oswald efficiency factor versus the angle of attack. And what we can also do is plot at the 5 degrees. So we can come drop this down here and come to 5 degrees. I'm going to reset this current graph. Reset. Nope. That's not what I meant to do. Reset graph scale. And so he wants plot the variation of the local lift coefficient. And that's what we are seeing across the wingspan. We are seeing a drop off at the edges of the wingspan and more of a lift coefficient towards the center, which matches the theory. Induced angle of attack, same idea here. Perfectly matches the theory. And lastly, the induced drag coefficient we can get here. And then you can export each of these graphs once again by going to current graph and export graph. And that was how I plotted multiple different wings with the different aspect ratios into Excel and plotted them and did a whole bunch of analysis on them. So I believe that was it for this video for the tutorial. So let me just double check, and it looks like we are good to go.